Here's a problem of elastic spring along an incline. We have a 50-gram block placed against a compressed spring with a spring constant that is equal to 640 newtons per meter, and it's along a frictionless slope at an angle of 40 degrees. When the spring is released, the block reaches a maximum distance of 1.8 meters along the slope, where it is not in contact with the spring anymore. What was the compression of the spring originally? So we have the equilibrium position of the spring somewhere here. I have marked it as x equals 0. It corresponds to the position where the spring is neither compressed nor stretched. Obviously, we start with the block somewhere lower than that location, so the question will be, what is that x? I'll use the symbol x for the compression, the original compression of the spring. We'll be using gravitational potential energy, for which we will actually need to choose a ground level. A natural choice will be to choose the lowest position of the block, so it's really where it starts. Remember, for the ground we are focused on the vertical elevation. Then of course we'll need the vertical elevation of the block when it actually goes all the way up to the slope, 1.8 meters along the slope. I'll mark that as y, and we can figure out the y by using trigonometry. I have here a right angle triangle, the hypotenuse of which is the distance 1.8 meters along the slope. I know that the angle between the slope and the horizontal is 40 degrees, so using the definition of sine from trigonometry, I can set up that the y, which is going to be the opposite side in this triangle, divided by L, which is the hypotenuse, will be sine of 40. In other words, once I put the numbers here in my calculator, the vertical elevation of the block will be 1.157 meters above what I chose as ground. Again, the ground here is the lowest position from which we start. Now we're ready to look at the total mechanical energy. At the top, the highest position, we have the mechanical energy will be the sum of the kinetic and the two potential energies. For kinetic, we're going to have 1/2 mv squared, but again, this is the turning point, and so that means that the block, this is the location where the block stops and starts sliding down, so my kinetic energy here will be 0. Then I'll have gravitational potential energy, mgy, and elastic potential energy, which will be 1/2 kx squared by definition. Of course, the block is not in contact with the spring anymore, so that will also be 0. In short, the total mechanical energy at the highest position of the block will simply be equal to whatever it has in the form of potential energy, mgy. Remember here, y is going to be 1.157 meters as we calculated using trigonometry. Now let's look at the energy at our ground level. That corresponds to the level where the block starts. We're going to have again kinetic plus 2 potential energies. The kinetic 1/2 of mv squared is once again 0 because the block starts from rest. The problem does not mention any initial velocity. We will also have the gravitational potential energy equal to 0 because of our choice. We just chose that will be our gravitational potential energy level there, 0. And then we'll have the elastic potential energy, 1/2 kx squared. I can apply the conservation of energy principle here, which stipulates that the energy at the highest position has to be equal to the energy at the lowest position. I have no non-conservative forces to change that energy. So, for our problem here will be the total mechanical energy at the top will be equal to the total mechanical energy at the ground level. In other words, we will have mgy, that's the energy at the top, equal to 1/2 kx squared, that's the energy with which we started at the level that we chose to be ground. With the numerical values given in the problem, I will have now the mass switched into kilograms, 0.05 kilograms, multiplied by g, 9.8 meters per second squared, and 1.157, the vertical elevation above my ground that I calculated. That has to be equal to the elastic potential energy at the lowest level, which is going to be 1/2 k, which is 640 newtons per meter, x squared. And this equation will give me the initial compression of the spring. Once I put all my the numeric values in my calculator, the initial compression of the spring turns out to be 0.0421 meters, or simply 4.21 centimeters.